In today's class, I will explain you about AVL tree introduction, and also I will tell you how the elements should be inserted into the AVL tree and what are the rotations are required. Then in last class, we had a discussion on binary search tree. Then what is the problem with the binary search tree? I will tell you once again. If the elements has been provided in ascending order or descending order, the height of the tree will be increased. And also the searching time will also be increased. Why? Because if the input has been provided 1, 2, 3, 4, 5, 6 like this, 1, 2, 3, 4, 5, here how you can able to construct the binary search tree. Then here already you know that all elements in the left subtree are less than the root, all elements in the right subtree are greater than or equal to the root. Then first element becomes the root, then the second element is greater than the root, that's why it has placed in the right subtree. Then like that you can insert 3, then 4, then 5. Is what is happening here, the height of the tree will be increased. Once the height of the tree will be increased, then what is the problem? The searching time will take more. That is the problem with BST. Then after that, if you provide the descending order like this 6, 5, 4, 3, then 2, 1, then now we can able to construct the binary search tree 6, 5, 4, 3, then 2, then 1. Here also the height of the tree will be increased. Okay, this is called as a right skewed binary search tree. This is called as the left skewed binary search tree. Okay, that is the problem with the BST. Then to overcome that problem, the height balanced binary tree has been introduced. Okay, which is also called as the AVL tree. Then in the next slide, then what is AVL tree? AVL tree is also called as the balanced binary search tree, because at the time of inventing the balanced binary search tree, the authors are Adelson, Veleski, and Landis. That's why the name was renamed as AVL trees. See over here, which was developed by Adelson, Veleski, and Landis. Then, if the binary search tree is said to be height balanced, if the height of the left subtree and height of the right subtree would be either -1 or 0 or +1. Those types of trees are called as the balanced binary search tree or AVL trees. Then whenever you construct the AVL tree, then you should able to require the rotations. Then what are the rotations are required? We will see in the future slides. Got my point? Then AVL tree is nothing but height balanced binary search tree. Then next slide. Then see here what is the definition of the AVL tree. The balance the factor of each and every node is either -1, 0, or +1. Those types of trees are called as what? AVL trees. If it is more than 1, then those trees are not belongs to the height balanced binary search tree, or which is also called as the AVL tree, either -1 or 0 or +1. Then how do you find the balance factor of each and every node? The balance factor can be defined as height of the left subtree minus height of the right subtree. For example, the balance factor of 25. Here the 25 is called what? 25 is the root node. Okay, here the 25 is the root node. What is the balance factor of 25? Then height of the left subtree. Then 1, 2, 3. Height of the left subtree is 3. Then height of the right subtree 1, 2, 3. Okay, how many edges has to be there? 3 edges in the left subtree, 3 edges in the right subtree. That's why what is the balance factor of node 25? That would be 0. Okay, like that you can able to find the balance factor of 36. Then where it is there, the balance of 36 here, then what is the 1, 2, the balance factor of the left subtree, the height of the left subtree is 2, the height of the right subtree is 2, 2, then the value would be 0. Then balance factor of 10, height of the left subtree is 0, then height of the right subtree is 1, the balance factor is -1. Okay, because there is no left subtree of 10, it has only right subtree. That's why 0 -1, the result will, the balance factor would be -1. Like that, you can find out each and every node in the tree. If not more than one, those types of trees are called as the AVL trees, which are also called as the height balance binary search trees. Then balance factor of 20 also. Then 2 minus 1. Here 1, 2 how many edges in the left subtree? 2. Then how many edges in the right subtree? 1. The 2 minus 1. The balance factor is 1. Okay, you can find out each and every node balance factor in the tree. If it is satisfies, it is less than 1, either minus 1 or 0 plus 1, it is called as the AVL tree. Okay, if it is not, what should we do? We need rotations to convert the tree into the AVL tree. We will see in the next slides. Then AVL tree insertion. Okay, how do you insert elements into AVL tree? We will see. Then there are four possibilities whenever insert an element into the AVL trees. The first possibility is that first case, the newly inserted node is the left child of the left subtree, that is called as the LL rotations. The newly inserted node is right child of the left subtree, that is called as the RL rotations. The newly inserted node is the left child of the right subtree, which is called as the LR rotations. The newly inserted node is the right child of the right subtree, which is called as the RR rotation. Okay, there are four rotation which has been supported by the AVL tree. The LL rotations, the RR rotations, RL rotations, then LR rotations. See here, how many rotations will be there? There are four rotation has been supported by the AVL tree. There are two single rotations. The LL and RR both are what? Single rotations. These two are called as single rotations. When you comes to the double rotation, two times we need to require the rotations. That's why the all LR rotations and RL rotation, which are the double rotation. We will see one by one. Then what is LL? What is RR? What is LR? What is RL? Then see here the LL rotation when it is happening, because whenever the node as inserted as the left node of the left subtree, then we can perform the LL rotation. See here, then where it has written, it has inserted left node of the left subtree, then we can perform the LL operations. Then see here, the example is also be given over here. Then if the tree is like this, then CBA, then what is the height balance? Then 2 minus 0. That's why the height balance factor is 2. Now it is not a AVL tree. Okay, it is not a AVL tree. Then we should perform LL rotations. Then how do you perform the LL rotations? It is a clockwise rotations which is applied on the edge of below node having the balance factor is 2. Because here we can perform the LL operation. Then we should rotate it to the right. Then see here, when it is rotated to the right, then node B becomes the root node. The node B becomes the root node. Then A would be left child of the B. The C would be right child of the B. Then the resultant tree is balanced tree. Okay, A, B, C. Then here the balance factor is 0. Here is the balance factor is 0. Here is the balance factor is 0. Then I will also give the example for it. Then LL rotation example. Then for example 30, then 20, then 10. Then this balance factor is 0. The balance factor is plus 1. The balance factor is plus 2. Because it is not a AVL tree. Then how do you say that whether is trees belongs to the AVL tree or not? If does not exceed in the more than 1, okay, then what is the balance factor of the node 32? Then it is not belongs to the what is called AVL tree. Then you should perform the LL rotations. Okay, then you rotate to the right. Okay, when it is rotate to the right, the 20 will becomes the root node. Then the 10 will becomes here. Then 30 will becomes here. Okay, when it is rotate to the right, then 20 will become the root node. The 10 will become the left child of the 20. Then 30 will become the right child of the 20. Then what is the balance factor of each and every node is here? Then 1 minus 1, then 0. Okay, this is called as the LL rotation. Whenever inserting the elements into AVL tree, sometimes it does not becomes the balanced, then we should perform the LL rotations or any other rotations. Then when it comes to the RR rotations, it is an anti-clockwise rotation. Then when it is happening, it is inserted as right node of the right subtree, then we can perform the RR rotations. The example is also be given because the balance factor is 0 minus 2. Then what is minus 2? Okay, this is minus 1. Okay, then we should able to perform, or it is not a AVL tree. To make it as AVL tree, then we should perform the RR rotation. Then we can rotate to the left. Then now it becomes the balance. Okay, then I will give the example for it. Then 10, for example 10, then 20, then 30. After that, I will also give the example for all rotations. Then here, what is the balance factor is 0. Then what is the balance factor is 0 minus 1. Then what is the balance? There is no left child. That is why 0. Then how many edges in the right child? Then 2, because the balance factor is minus 2. Because now it is not a AVL tree. Then what you have to do? We should perform what is called RR rotations. Then we rotate to the left. That's why then here whenever it is rotated to the left, then 20 will become the root node. Then the 10 will be left child of the 20. Then 30 would be right child of the 20. Then what is happening over here? Then it is balance factor is 0. The balance factor is 0. Then it is also left child minus 1. 1 minus 1, the balance factor would be 0. Now it is called as AVL tree. The previous one, it is not a AVL tree because whenever 30 has been inserted, because now it is imbalanced, it is not balanced, unbalanced, because then how should we make it as a balanced? Then we should perform the RR rotations. Got my point? Then I move on to the next rotation, LR rotations. Okay, it is type of double rotations. Then first you should perform, it is a combination of RR and LL because RR followed by the LL. Okay, for 2 times you can do the rotations. Then first you should perform the uh, LL rotations, sorry, RR rotations. Then we should perform the LL rotation. In such cases, then example has been given over here. Then here this balance factor is minus 1. That's why 0 minus 1. Then here the balance factor is 0. It is minus 1, it is plus 2 because there is no right child for the C. Then it is not a balanced. Then how it is make balanced? Then we should perform the 2 types of the rotation. At this time, then it is rotate to the left. After that, it is rotate to the right. When it is rotate to the left, that is called as RR rotations. Now B will becomes here, the A will becomes the left child. Okay, the resultant tree here because it is also not becomes the AVL tree. Then at that time we should perform the LL operations or LL rotations. Then here now once you perform the LL rotations, the B will becomes the root node, the A will become the left child of the B, then C will become the right child of the C. The result is given. Now it is called as the AVL tree. Then here it is not a AVL tree. Then finally we performed the 2 rotations. Finally we got the AVL tree. But it is not possible with single rotation to make it as a balanced. Okay. Then I will give the example for it. The example is like this. Then 40, 20. Then what is the balance factor is 0. Then balance factor is minus 1. The balance factor is plus 2. Then what should do here? Then first you should perform the RR rotations. Okay, then once you perform the RR rotations, then here once you perform the RR rotation over here, then what is happening? What is the resultant tree? Then 40, then 30 will comes here, then 20. Okay, here you should perform the RR rotation over here, then 0, then plus 1, then plus 2. Okay, this is it is also not becomes AVL tree. Then we should perform the LL rotations. Okay, then first we should perform the RR rotations, then we need to we can perform the LL rotations. Then what is happening? Then we should perform the LL rotation, rotate to the right, then 30 will becomes the root node, then 20 will becomes here, then 40 will becomes here. Because 20 is the left child of the 30, then 40 is becomes the right child of the 30. Then now you can check balance factor of each and every node, then 0. Now it is becomes AVL tree. Previously it was not AVL tree. Now how you can make it as AVL tree? We should perform the two rotations RR followed by the LL. Got my point? If you want to complex problems, you can contact me at any time through comment box. Then next rotation is RL rotations. Then here it is a combination of LL followed by the RR. We should perform the LL is first, then we should be able to perform the RR rotations. When you perform the RL rotations, if the insertion is like this, okay, ACB, then the balance factor is 2. That's why it is not AVL tree. Then first, what you have to do, then we can perform the LL rotations. The resultant tree is like that. Then after that, we can perform the RR rotations. Now it is a balanced AVL tree. That is a balanced binary search tree or AVL tree. Okay, this is the way we can make it as a balanced binary search tree by using the RL rotation. I will also give the example for it. Then if it is like this, then we need to find out the balance factor of each and every node. 0 plus 1, here minus 2, because there is no left subtree. There is 2 edges will be there in the right subtree. That's why the balance factor of node 30 would be 2, because it is not a able tree. Then what you have to do here? Then we should perform then what is called LL rotations. Then LL rotation will be performed first. Then when you perform the LL rotation over here, then what is the resultant tree? 30, then 40 will be comes here, then 50. Then again after that you need to find the balance factor of each and every node, then minus 1, then minus 2. After that, it is not a AVL tree, then we should perform the RR rotations. Then we can rotate to the left, then 40 will becomes the root node, then 30 will become the left child of the 40, then 50 will become the right child of the 40. Then you need to check the balance factor of each and every node, 0, 0, then 0. Now it is AVL tree. Yes or no? Because how many rotations are required over here? Then this is the first rotations. This is the second rotation. We should perform the LL rotations first. Then we need to perform the RR rotations next. Okay, they are the way we can use any one of the rotations. Then we make it as a balanced. Okay, that's why which are called as the balanced binary search tree. Then I move to the next example. Here, this is the elements I would like to insert into the AVL tree. Then 63, then 93, sorry, 63, 9, 19, 27, 18, 108, then 99. Okay, then how we can able to insert these elements? For 63, okay, the 63 is a root node. The insertion as usual, we can use the binary search tree. All elements in the left subtree are less than the root. All elements in the right subtree are greater than or equal to the root. When it is not balanced, then we can make it as a balanced. The 63, there is no problem. It is a balance factor is 0. Then it is becomes the AVL tree. Then 9 has been inserted. Then now it is also becomes AVL tree. Then balance factor is 0 and 1. Whenever you insert it the 19, now it is not a AVL tree, because the balance factor is 2. That's why it is not a AVL tree. Then what you have to do is, then we should perform the RR rotations first. Then which rotation is required? Then you think of it. Okay, then you can use the suitable rotations, make it as a balance. Then here I would like to use the RR rotations. Then 19 RR rotation to be performed. Then 9 will becomes here. Then 19 will the left child of the 9. Then again after that you should be able to find out the balance factor of each and every node. This is the 0. This is the -1. This is would be 2. Then after that, it is also not a AVL tree. Then we can perform the LL operations. Then we should rotate to the right. Now, whenever you should rotate to the right, then here what is called 9 will becomes the here 19. Okay, sorry to say the 19 will comes here, the 9 will comes here. Okay, the problem in the diagram here, whenever you perform the rotations, the 19 will comes here, the 9 will become the left child of the 19. Okay, then after that you should perform the LL rotation. 19 will become the root node, the 9 will become the left child of the 19, then 63 is the right child of the 19. You can find out the balance factor each and every node. Now the balance factor is 0, the balance factor is 0, the balance factor is 0. Now it is a AVL tree. After that, you should insert the 27. Now, whenever the 27 has been inserted over here, the balance factor of each and every node not more than 1. Now it is becomes the AVL tree. There is no problem for it. Then whenever the 18 has been inserted, then now it is the height balanced binary size tree. No rotation is required. Then I move on to the next step. Then whenever the 108 has to be inserted, then here no rotations are required. Okay, no rotations are required. Then now it is also AVL tree. Then whenever inserted the 99, then you can find out the balance factor of each and every node. Then it is not more than 1. It is also called as the AVL tree. Then whenever you inserted the elements into the AVL tree, then you check after insertion, then you can check the balance factor of each and every node. When it is not becomes the balanced, then you can use the suitable rotation. Either you go for the LL rotations or RR rotation, LR rotations or RR rotations. Okay. In this next slide, I move on to the next slide. Then how you can able to construct the AVL tree by using this sequence order 1, 2, 3, 4, 5, 6, 7, 8 to construct the AVL tree. The problem is given to you. They can try it once. If it is not getting, please connect me through what is called comment box. Then I will try to solve your problem. Okay. Then thank you all. Thank you for watching my videos. If you have any queries regarding this concept, please connect me through comment box window. Thank you. Thank you all for watching my videos.